record. Okay, so I don't have it on the announcement slide, but I will go ahead and mention the FE review sessions. The first one already happened, right? So hopefully that went well. You've got a few more coming. 3 of them are going to be from yours truly. I'm doing one on statics, and I'm doing 2 on mechanics of materials. So it's like a part 1, part 2. So, yeah. There actually isn't one specifically dedicated to structural analysis, because usually the structural analysis on the exam is a mixture of statics and mechanics. You know, there's a little bit like maybe influence lines and whatnot, but it's just not a lot. If you can do statics and mechanics, you should be pretty good. Okay, I'm a little behind, I will admit, on like updating attendance and whatnot. That's just something I'm going to be taking care of in the next couple of days. But I'm going to count everybody present for the last lecture, because that was virtual and you didn't really have an opportunity to be there or not. So for those lectures, I've decided I'm just going to count everybody present. What should be up on Blackboard are all the solutions up to 2.3. I need to check and see where we're at on grading. I just didn't have time to do that before class today. I got here and I've literally been in a meeting since. Like I've been basically since 8 a.m. back to back meetings until right now. And I've got meetings until then, until about 4:30 today. So, yay. So today what we're going to do is, it might seem a little superfluous, but I have found that it's valuable. We are going to do just another tension member example, tension member design. But the tension member design that we're going to do is basically your last homework assignment. Different member, different loads, different bolts, etc. But I have found that in this course, when you first start doing design, it takes some getting used to. And I found that by doing just another example, particularly one that's very similar to the homework that you just did, it helps it click a little bit. So that's what we're going to do. Okay, now let's okay, I didn't want to do that. Let's just, oh, come on. Let's do that. Okay. So this is the step-by-step process for design, which, by the way, like I said, I'm a little behind on Blackboard. I haven't uploaded these notes yet, but I will by today or tomorrow. So this is the step-by-step process for design. And I want to be clear, this is the step-by-step process for tension members. We're going to have different processes for columns and beams and so on and so forth. I do think that this is a very, very good place to start, because just about every single tension member course, steel design course at any institution, any university, tends to start with tension members, because it orients you to the basics of design. So the way that it works is we start off, we get our factored load, we compute our 2 values for design. Now what we're doing is we're using our denominator as the minimum of 0.9 Fy or 0.75 squared times Fu. So the reason for the 0.9 is that's our resistance factor, and for the 0.75 squared, one of those is our resistance factor. The other is the assumption that we're making for the effective net area. We're saying the effective net area is about 75% of the gross area. That's why there's 2.75s. And so we pick a member that has a gross area at least bigger than that, and a radius of gyration at least bigger than that. So based on that, and based on any other problem constraints, which you are already pretty familiar with that, we did the example on the pre-record that said select a channel, and that might have seemed like, oh, there's a lot of channels. There actually aren't. There aren't many C-shapes in the manual, right? Now, W-shapes, that's different. That's why your homework was limiting you to W8s, I believe it was. So we're going to do a problem today limiting you to W12s. So based on the problem constraints, select the lightest shape that you can, and then we're going to analyze that shape. And that is very, very important, because of this right here, we're making a lot of assumptions about net section fracture. And so we, quite frankly, just need to analyze it to ensure that the shape is efficient. Speaking of efficiency, the showcase showdown, or the Price is Right spinning the wheel. We want our efficiency to be as close to 1 without going over. Specifically, a good rule of thumb for tension members is that if you're about 90%, you're good. Okay. Finally, I will mention the limit states. I'll have these here because this is step 4. We have to go through it and analyze this. Starting on Friday, we're going to start talking about block shear. Block shear is different. It's kind of quirky, so I will leave it at that. All right, here's our problem. We're going to select a W12. So it's a W12 by something. Your homework assignment had a W8 by something. So the process is going to be very similar. I switched it up a little bit. We have 7/8 inch diameter bolts. So different. So we have 2 lines of bolts in each flange. The bolts longitudinally are spaced 4 inches apart. 3 bolts per line. Dead load of 130 kips, live load of 110 kips. Let's pick a member of A992 steel. Let me go to the notebook. Everything's there. I'll give everybody a sec to write this out. Everybody good? Now today, I did not bring my AISC steel construction manual, which means I'm going to need your help, which means I'm going to rely on the manuals that you brought with you today, right? Because everybody brought their 15th edition AISC steel construction manual, right? Me? I don't see it. Well, you're the only one I don't see that has the manual. It's in my backpack. Oh, okay. You saved yourself on that one. Okay. I don't know about that. Okay. Step 1. Okay, so what is step 1? Well, you tell me what step 1.
Make it really big. It was to get the load.
Yeah. But make it really big. Can everybody read this?
No, I mean just make the number really big.
Oh, yeah. Like the W12 by 800, it works. You go, for what? It doesn't matter. It works. The W12 by 800, it works. The efficiency might be like 0.4%, but it works. So before we move on, I hope that this was clear on the homework assignment. I think for some of you it might not have been. There are 2 words which are interchangeable in structural engineering, and those are unfactored and service, right? So a service load is a load that is unfactored. So if we are computing a factored load, this dead load of 130 kips and this live load of 110 kips would be considered service loads. Okay? And so all that means is, like, actually what is the load that the member is experiencing. So let's do some math and we'll be able to put this in context. Say it again.
332.
Do I have a second on that? Okay, all right. So let's put this into some context. I want to make sure that everybody understands what's going on. I'm going to ask you a simple question. How much load is actually being put on this tension member?
240 kids.
240 kids. How much are we designing it for?
332 kids.
That's the difference. Does that make sense? We are actually putting 240 kips of load on this tension member, but I'm designing it for 332. We are upping the loads according to their respective uncertainties. I am more certain about the magnitude of this dead load than I am the live load, which is why I am augmenting the live load more. The live load has a load factor of 1.6. Dead load has 1.2. Or I can estimate the amount of dead load on a structure with some fairly reasonable certainty, but live load, that's a little different. It's kind of hard to estimate the floor load in a classroom because when we leave, there's going to be another class coming in, different loads. Make sense? Okay. So, in order to compute our necessary design parameters, the AG design and the R design, we're going to need FY and FU. So, this is A992 steel. So, what is FY and FU respectively for A992 steel?
FY 50 and FU 65.
That's exactly right. Now, again, as I've said before, I'm totally fine with, as we first start learning the science of steel design, that, look this stuff up. Later on, it's going to kind of be better for you if some of these values you kind of remember. And I would argue the two most common steel grades that we will use in this course are going to be A992 steel and A36 steel. Those are going to be the two most common ones. So I'm not saying that I won't throw another one at you every now and then just for the heck of it, but those are pretty common. And what I can tell you is that when we get to column land and beam land, when we start designing columns and beams, this is like the only one we're going to use. So just saying. Okay. So what we're going to do is we're going to handle this the way that I did on the video is off to the side. I'm going to compute 0.9 FY .9 times 50 is what? And 0.75 squared times FU. So what is that? And that is enough. One of the things to keep in mind, what we are computing are essentially some guides to help us select the member, right? But, you know how the members are discretized in the manual. So there's a point when the accuracy is good enough. So AG design equals that. What goes on the bottom? That one, right? And so what is this?
9.08.
Say it again.
9.08.
Do I have a second on that?
Yes.
And so we also need our design, which is L over 300. How long is this member? So, is that right? Well, I mean, it'll give me an answer, but the answer will be in feet, right? And so what does this come out to be? 30 over 300 is 0.1. 0.1 times 12. Okay. I'm going to stop for a sec. First off, do you have any questions about what we've done so far? Second, do you have any questions about what you did on the homework assignment? And is there anything that we've done here that has helped clarify things? Now, we need to select a trial shape. Let's see. There are 3 constraints that I know of. First, second, we'll say R min must be greater than or equal to 1.2 inches. What's the third constraint? It has to be a W12, right? So now I want everybody to break out their AISC 15th edition steel construction manual and help me out. If I'm selecting W12s and I'm limited to this selection criteria, what is the lightest shape that you can find that meets these 3 requirements?
W12 by 35.
W12 by 35. Do I have a second on that? Okay. Now, it is a trial shape because we have to analyze it. Let's see. All right. Let's try a W12 by 35. Now, we're going to need some properties. First off, what is the AG? So that meets the first requirement. The second one, now what's the smaller of the R values? RX or RY? RY. So, what is that? Okay. What other dimensional properties are we going to need for this shape? Thickness of what? The flange. What is that? Now I'm curious, can anybody look into the crystal ball and see there's 2 more properties that we're going to need for this shape? BF and D, right? Because we need that for the for the shear lag factor. We need the BF and D. So what is BF for W12 by 35? And D? All right. Now before we start doing math, is there any other property that you think we're going to need? There you go. Okay. So So what is the equivalent WT in this instance going to be? And it's the Y bar, right? One of the things that I like to do, and you get better at this with practice, just trust me. But when you're in design mode and you know you got a trial shape, just look up everything before you do any math. Just do it all, you know, you'll save time, trust me. So like, I could have just wrote down the W12 by 35, and then I say, okay, I need to compute the net area. Oh, let me get the flange thickness. I need to compute the shear lag factor. Oh, I need the BF and D. Oh, I need the Y bar. Oh, I need the R value to get the slenderness. Just look it all up. Make your life a little easier. So what's the Y bar for the WT 6 by 17 and a half? Any questions? Now remind me, how much load does this member, or how much is it designed to withstand? Okay, 332 kips. So it's designed to withstand 332 kips. Let's see if it has a capacity of 332 kips. Yes, sir.
On, like, in the steel manual where you find, like, the PDF and, like, the thickness, there's two columns. There's, like, for the 12 by 35, it says, 6.56, but then next to it it says 6.5, like, in a fraction.
Mm-hmm.
Is that just, like, what they go off of, like, in, like, professional? Or
Can somebody else answer that for me? Yeah, one is for design and one's for drafting.
Okay.
So, yes. Wait, what? That's a great question. Let's see. Okay. So the question is, do we need the flange thickness or the web thickness? So here's the member. So where are the bolts going through? The bolts are going through the flange, which is why we looked up that property. So if we had bolts going through the web, then we'd use that one. Which, by the way, that is also a very common way to connect tension members, is bolts through the web as well. That happens all the time. So this is good stuff. This is the stuff I want you to ask. I don't want you to get, it's really easy in this class to get into this like methodical, I'm just doing this because this is what Dr. Mike did. You know, I don't want that to be the case. I want you to know what we're doing and why we're doing it, okay? I find that steel design, routine steel design is pretty easy, but it's also, because it's easy to fall into this, well, I just did that because that's what we did in the in-class example, okay? And I don't want that to be the case. Any questions? This is good stuff. All right, so now let's analyze this trial section. And we are going to talk about what happens at the end of this problem and what you should do given certain outcomes. Now, what does it mean to analyze the trial section? We need to look at gross section yielding capacity, net section fracture capacity. We can honestly do the gross section yielding right now. We know the FY, we know the AG. We can just compute that right now. Personally, what I like to do is compute the net area, compute the shear lag factors, and then just do both of those at the same time. But it doesn't matter. You can do them in whatever order you'd like. I'm going to start, though, with the net area. How do I compute the net area for this? I'm asking you. How do I compute the net area for this shape? So, the gross area minus 4 bolt holes. 1, 2, 3, 4. And you are computing those bolt hole areas by taking the hole diameter times the flange thickness, right? So what you're doing is saying, well, I already put the equal there, AG times that. And to get the hole diameter, we take the bolt diameter and we add what? 27 inch. So the bolt diameter was 7/8 of an inch. So that makes a hole diameter of 1 inch. What do we get for this? Say it again? 8.22. Do I have a second on that? Let me highlight this, just so I don't have to go on a hunting expedition later. Shear lag factors. Which cases are going to apply for this member? 2 and what? 2 and 7. What is X bar for this connection going to be? 1.3. It is the Y bar for the equivalent WT. So I'm actually going to put Y bar here. Y bar 6 by 17.5, and then this is just LCON. How long is the connection? 8 inches from center of bolt, center of bolt. And so what is this? Say it again.
18375.
We'll say like 838. Now, do we have K7 applicability? What does K7 say? For W, M, S, or HP shapes, or T's cut from those shapes. So we're good there. There's 2 branches. The upper branch says with connected by the flanges with how many bolts per line? 3 or more. Do we have 3 or more per line? How many do we have per line? 3. 3 per line. So how does this case work? We compare BF and 2/3 of the depth. What is that? So BF and 2/3 depth, that's greater. So what is U7? Say it again. So between this value and this value, what's U? Say it again. And again, highlighted. So now we've got everything that we need to do our analysis. So there's 3 checks that we're going to do. Gross section yielding, net section fracture, slenderness. So one at a time. Then this is 10.3. What does that come out to be? Now, I'm going to hold off for a sec because I want to explain something conceptually. Let's go back to the loads. How much load are we putting on this tension member? 2. Hold on. Hold on. What I asked was, how much load are we putting on this tension member? 240 kips. How much are we designing it for? Okay. This number is how much usable capacity we can count on according to the gross section yielding limit state. Can it hold up more than this according to gross section yielding in real life? What is the capacity according to gross section yielding? It's FYAG. What is 50 times 10.3?
503.
Say it again.
503.
503?
Yeah.
Okay, so 50 times 10.3 is 503. I propose that the member can hold up 503 kips according to gross section yielding. But we're only going to be able to count on this much. Does that make sense? Everybody okay with that? All right, I want to make sure that that works conceptually. See, the thing about LRFD is you're taking those nominal resistances and service loads. You're bumping up the loads and you're lowering the resistances. That's what these 0.9 and 0.75s are doing in the 1.2 dead and 1.6 live. So. So that's the U value. This is the AN. And notice I highlighted them, right? So you can see where I got it. That was why I broke out my highlighter so you can see all this. So what do you get for this? Okay. Yes?
Why do you have to cut down the net area more than the gross area?
That's a great question. You're talking about the phi values? Yeah. That's a great question. So the question was, why do we have to cut down the, like when we're computing our limit states, why do we have a resistance factor of 0.9 for yielding and 0.75 for fracture? The answer is what they represent. What happens if you exceed gross section yielding? Like in reality, what happens? So permanent deformation. So the member gets longer. That will induce unaccounted for stresses in external members. But it doesn't mean the member is snapping in half. What does net section fracture mean? Boom. It is a more dangerous event. Does that make sense? That's a really, really good question. Okay? It's a really good question. Yes?
Just in general practice, would it be, like if you wanted to round to that 340.62 to the nearest one, you would round it down, right?
That's a good question. Honestly, I'd probably round it up, honestly. I mean, but in practice, this is what I do. I would probably round it like I would round any normal number to the nearest like tenth of a kip, because past that, you're good. You know?
It's cool enough that it doesn't really.
We're talking about, think about the context. We're talking about 340,000 pounds, and I'm saying to the nearest 100 pounds.
Okay.
That's good. So. I've had homework assignments where students will say 340.613865326112. You're getting to like the atoms, Like, you're not that good. Nobody's that good, you know? So. Which one of these controls the design? The lowest, because if I yank on this, this is the load I'm going to hit first. So this governs. Now, before we summarize everything, we got one more. So what does this come out to be? And I'd say to the nearest tenth is probably fine. Usually when I'm doing columns, though, when I compute slenderness, it's like to the nearest hundredth and whatnot, because it's a little bit more important in that world than it is for this. Second? Okay. So I want to summarize. So PU was what, 332 kips? Again, we're actually putting 240 on it, but I'm designing it for 332. Its usable capacity is this. Even though it can probably hold up more in the real world, I am bumping it down a little bit, again, for safety, for the uncertainty. Now, is this member good? It is. Now, how can we express that numerically? And this probably goes without saying, but you can multiply this by 100 to get it in a percent. And by the way, while we're waiting on that, we know the L over R is less than 300, so we're good there. Say again? 97.5%. So, is this a viable member, a good design? Of course it is, yeah. So what's the answer to the problem? Now, let me ask a question. What if this was 103%? What would that mean? Whoa, hold on. Larger member. The next larger up. That means the member's too small. You are 100% right that we got to repeat the process. So let's dig into that a little bit. If that number was 130%, let's think about what that means. The factored load is more than the factored resistance. We're putting more load onto it than we can withstand. And I say that with the context that those factors of safety are built into that those observations. So that member would be no good. So what do we do if we have a W12 by 35? We pick the next one up, which is a W12 by what, 40? Is that the next one up? I think it is. But what does that mean, repeat the process? Does that mean start back at step 1? I'd say step 4. I mean, step 3, we selected the member, so this was selecting the trial shape. So we just pick the next one up, so W12 by 40, WT6 by 20, and just do it again. And then, here's the thing. Now let's live in some reality. What if I picked the next member and the efficiency was 85%? What does that mean? But there is, the next smallest member didn't work. Say it again. Just use it. Exactly right. Again, the 90% is a good rule of thumb. It's not perfect. I didn't say it was perfect. I didn't say any of this stuff was perfect. I'm talking about real life, okay? What if you pick up the phone, you call a service center, and they don't have any W12x40s on stock, but they have the next highest one up? There you go. Just use it. Okay. Before you all leave, does anybody want to see something kind of crazy that we're going to deal with next time? So, let me show you something before we leave. This is something to get you thinking. This is from last year. Check this out. So, this is the limit state that I've been talking about that we haven't added yet. This is what's called block shear rupture. What happens is you're yanking on a member and you rip a chunk out of it. You failed part of it in shear, part of it in tension, and you literally are ripping a chunk out of it. It's actually discovered by accident in the lab. They were doing some tests on some members in a lab in Canada, and I guess what happened was the grad student went to their professor and said, "So this happened." What? Do it again. Did it again, and it happened again. So, random factoid for you. You were going to say something? Did somebody say something? Oh, okay. Now, let me show you something. So, what happens with block shear is that block shear is defined as a combination, a failure path that combines both a region that's failing in shear and a region that's failing in tension. Okay? So, for example, if I was considering this failure path or this failure block, the failure block has two shear paths, one tensile path. And with either of those paths, there are gross areas and net areas, etc. Now, if you open up the spec, this is what the equation looks like. Way longer than 0.9 FYAG, right? It's way longer. But you'd be surprised how basic this is, okay? And we'll talk about this next time. But first off, you can simplify this algebraically by factoring out a lot of the common terms. But if you look at the equation, a lot of this is stuff we've already been dealing with. AGAN, AGAN. It's just the net area and gross area in shear, the net area and gross area in tension. FY, FUs, etc. There is one number that's sort of thrown in there, which we'll talk about next time, this 0.6. I have asked on exams, why is that 0.6 there? And what happens invariably with about half the class is I tell them what that 0.6 represents, and then it's on an exam and they can't remember. So they say something like, I don't remember, but I'm going to say something that sounds smart. I'm going to say it's a factor of safety, and it's not a factor of safety. So this is me telling you that if I happen to put a problem like that on the exam, and you say factor of safety, that's wrong. What's points are you looking at? I'm sitting here telling you that like this is something not to do on the exam in the event of getting points, and your answer is how much is it worth? This is literally me saying, don't do this on the exam and you'll get credit. And he's like, but that takes a lot of brain power to remember stuff, Dr. Mike, so I need to know how much this is worth. You know?
What is its purpose?
We'll talk about it on, we will talk about this on Wednesday. Yes, I am.
But now you have it in our brains, the association between that and a factor of safety.
It's not. You'll find out what it is. You'll find out. Trust me.